Hey everyone. So in this video, let's take a look at what it means to be continuous on an interval. Now we've already talked about continuity at a specific point. Well, if we want to take a look at continuity at an interval, we're just going one step further. So for a function to be continuous on an interval, it just needs to be continuous at every single point within that interval. So let's just start out by taking a look at a couple examples of the intervals that we're going to be using. So the first one is the open interval. And let's say that we're looking at this open interval in between two numbers, and let's call them A and B. The way we notate this is with parentheses and then A comma B. So this is the open interval from A to B. To take a look at what a graph of this would look like, we have our two numbers A and B, and then our function is going from A to B. But the open interval means that we're not including A and B in our interval. So to indicate that on a graph, we're going to have two open circles. So our function is getting up right next to these two values, but not quite getting there. And in between, our function can do whatever it needs to do. So for a function to be continuous on the open interval, it needs to be continuous for everything in between A and B, but not A and B. We also have the closed interval. And again, let's say we're looking at the closed interval from A to B. The difference here is that we are going to include A and B in our interval. So we'll use brackets on A and B to indicate that we do want to include those in our interval. So now in our graph, we'll use closed circles, closed points to indicate that. So for a function to be continuous on the closed interval, not only does it need to be continuous for everything in between A and B, but it also needs to be continuous at A and it needs to be continuous at B. We can also mix and match these as well. So our other intervals, we would have not including A, but we can include B. So that would look like this. Or the other possibility is I could have including A, but not including B. And that would look like this. So in these two cases, just like the first one, the open and the closed, our function does need to be continuous for everything in between A and B. But in this one, it's not going to be continuous with this right-sided limit as we approach A, but it will be continuous as we approach B and including B. And then just the opposite for our second one. So our right-sided limit as we approach A, that's going to exist, and that'll be A. But our left-sided limit as we approach B, it's not going to be continuous there. So now let's take a look at an example where we want to figure out whether or not a function is continuous for a specific interval. So here's my example. I have f of x is equal to the square root of 4 minus x squared. And I want to determine whether or not this is continuous on the closed interval from -2 to 2. So we can still use our three-part definition of continuity to help us test this out. The first piece of that definition was that our values have to be in the domain of our function. So let's take a look at the domain of our function first and make sure our interval is in there. So my function, I have a square root in here, so I know that's my restriction. So I just can't take the square root of any negative numbers. So I just need to make sure that everything under the square root sign, we need this to be greater than or equal to 0. So let's solve this inequality then. I can subtract 4 from both sides. And then I'm going to divide by -1. When I divide by a negative, I do need to switch the sign. And now taking the square root of both sides, we end up with x is less than or equal to plus or minus 2. Well, that plus or minus within an inequality is a little confusing written this way. So we can write that as a compound inequality instead. And I could say that x is in between -2 and 2. So my domain for my function, I'm going to write this in set builder notation. My domain is all x such that -2 is less than or equal to x, which is less than or equal to 2. All right, so that takes care of the first piece, because looking at the interval I want to test, I just want to take a look at everything in between -2 and 2, which is exactly what my domain is. So the second piece of the definition for continuity is we need to know that the limits exist. So we're going to do this in parts. So let's take a look at the open interval between -2 and 2 first. So what we want to do is we want to look at the limit as x approaches some number within that interval. So in this case, c is going to be any number that's in between -2 and 2. And we want to look at the limit as x approaches that. So this is the same then as the limit as x approaches c of the function, so the square root of 4 minus x squared. Now from here I can use some of my limit properties to rewrite this. So we do have a property for roots. So this is the same as the square root of the limit. And here I'm taking the limit as x approaches c of a polynomial. And we know that with any polynomial, to evaluate the limit, I can just substitute in the value. So then this is going to be equivalent to the square root of 4 minus c squared. Well, 4 minus c squared, that is exactly what f of c would be. So because the limit as I approach c is equal to the function value at c, I know that this is continuous for all the numbers that are in between -2 and 2. So to summarize, so f of x is continuous on that open interval from -2 to 2. So then the last thing we need to double check is our two endpoints. So what's happening at -2 and what's happening at 2. And to do that, we're going to look at our one-sided limits. So first, let's do the limit as x approaches -2. Now, just thinking about our interval, we don't have anything that's less than -2, so we're only approaching -2 from the right. So we're going to look at the right-sided limit as we approach -2. For our other endpoint, we want to take a look at the limit as x approaches +2, but then using a similar argument, we don't need to worry about any of the values that are bigger than 2, so we're only going to approach from the left. All right, for both of these limits, we can substitute in our value to evaluate them. So for the first one, we end up with the square root of 4 minus -2 squared. And for our second one, we end up with the square root of 4 minus 2 squared. Simplifying these expressions, we end up with 4 minus 4, which is 0. And in the second one, we also end up with 4 minus 4. So this is the square root of 0, which is just 0. And then the same thing on this one. Now, it's important that we ended up with 0 here, because that value is what we would get if we do the function value of f of -2, and it's what we would get if we plug in +2 as well. So in that case then, our limit is equal to f of -2, and the limit as we approach 2 is equal to the function value at 2. So that means that this is continuous at our 2 endpoints as well. And then bringing all of that together, we have our function is continuous on the open interval in between -2 and 2, and we have it's continuous at our 2 endpoints. So that means our function is continuous on the closed interval. So I'm going to say, therefore, f of x is continuous on the interval -2 to 2.